Today we're on the Chapter 15 AP Chemistry packet on page 8. We're going to be talking about a titration curve of a weak acid with a strong base. So we're going to start with the weak acid in the flask. It's acetic acid. We know the molarity, we know the volume, so we find the moles of that. Then we're adding to that the NaOH, which is going to be in the burette, and that is going to be 0.2 molar according to this problem. So there's going to be a sketch of this. It's going to look like this. If 7 is neutral and 7 is in the middle, we know we have a weak acid, so it's not going to be super low, but we're ending with a strong base, which is going to be pretty high. And if you look at your equivalence point right here, you're going to notice that it's going to be slightly basic, and that's going to be the equivalence point. Okay, there are going to be 4 main parts of a titration. The first part is going to be the initial pH of the weak acid by itself. Then you're going to have the halfway point, which is right here. The equivalence point is going to be right there, so the halfway point is halfway. And then we're going to do a little bit past the equivalence point, about 1 milliliter, let's say. So the first thing we want to do is focus on the equivalence point. Let's just do that first, and then move on from there to get our bearings. So remember how we do that. You could either use the equation NAVA equals NBVB. So NAVA equals NBVB. The normality of the base is the 0.2. It's the same as the molarity because there's only one OH in that base. The acid is a 0.1, and there's only one H in that comes off as an acid. So that's also 0.1 normal. We're using 50 milliliters, so I'll just use milliliters since it's a little easier. And then what we're going to do is find out how many milliliters do we need to titrate that. And we're going to find out that the answer is 25 milliliters. So that's going to be the equivalence point. Whenever you use this NAVA and BVB, you're trying to find the equivalence point. So right away you know that 25 is the equivalence point, so 12.5 is the halfway point, and this is 0. And so you could see that right here. The halfway point is 12.5, and then the equivalence point is 25. You kind of want to get your bearings in a titration before even starting the problem to know at what point of the titration you're doing your calculations. So let's start at the beginning. In the beginning, I only have a weak acid in here, a weak acid by itself. So if I have a weak acid by itself, how do I handle that? Ice and Ka. So I do ice, set equal to Ka, look for X, which is the H, negative log that, and you're going to get 2.87 as your first pH. So 2.87 is the beginning of this. All right, I'm going to try to do that in red just to highlight that as an acid. Okay, so we're going to write 2.87 here. 2.87, try that again. 2.87. That's our initial pH for the weak acid. Okay, now we're going to start putting in the NaOH. The moment you drop an NaOH drop into here, there's going to be a reaction. So you're going to do stoichion moles. So stoichion moles is always going to happen past the first 0. Okay, 0, there's no reaction because you haven't added it yet. But as soon as you add something, you're going to have stoichion moles. So let's just go right to the halfway point. Just to save time, we're going to focus on the halfway, the equivalence, and then past it. So we're going to go to here, 12.5 milliliters of NaOH. So you need to find out how many moles that is. So you're going to do your molarity equals moles over liters for your NaOH. You already started, you knew with this many moles of H+, sorry, not H+, but HA. So the running out is going to be the OH minus the limiting reagent in this case. So this runs out, and you have 0.0025 of this and 0.025 of that. So you have a buffer because you have a weak acid conjugate base. And when you use the buffer shortcut, you're going to see that these two are going to divide out, and the H plus equals the Ka. And you negative log that, and you get 4.74. That's always going to happen at the halfway point. The halfway point is when you've titrated half of this. So that means half of it is still here, and half of it is right there. And so now you have the halfway point as that number. Okay, so at the halfway point, this is very important. At the halfway point, the H plus equals the Ka, or the pH equals the pKa. Okay? Really important to understand that at the halfway point when you have a weak acid or base involved in the reaction. Okay, so that's the special thing about halfway. Now let's go to the equivalence point. You know what's special about that is that the moles of the acid are equal to the moles of the base. You've added exactly the right number of volume of milliliters of the base to match the acid. So they both run out. So these both run out. They're both 0. And so now all you have left is A minus, and A minus is a weak base. How do you handle a weak base? We do ice and Kb. Now remember, ice has to be in molarity. This is a big thing that a lot of students forget. You're so used to doing stoic in moles that you forget that ice has to be in molarity, which means you have to take these moles that we got and divide it by the total volume. The total volume. So we added 25 of the base. We originally had 50 of the acid if you look at the top of the page. So 50 plus 25 is 75 milliliters. So you have to use molarity for this. So then you have your ice equation set equal to Kb, but we already knew our Ka, so we have to find that. And then we throw it in and we get X. But X is their OH minus, remember, see? Not over there. X is over here. X is over here, our OH minus. So now we negative log and then 14 minus it. And so our final pH at the equivalence point is 8.79, which is slightly basic, which makes sense. So let's fill in these pHs over here. The pH at the halfway point was 4.74. This was 8.79, which again is slightly basic because of the presence of the acetate, which is the conjugate base of the acetic acid. So this is basic because there is a weak conjugate base at the equivalence point. That was the leftovers. Okay, now we're going to go 5 milliliters past the equivalence point just to see what happens. So 5 milliliters instead of 25, we're going to do 30. So 30 milliliters past, or 5 milliliters past, which is 30 total, gives you an 0.006. So that's the moles of this. And you can see that that's going to be more than the original acid that you had. So now you have leftovers of the OH minus. And you also have a bunch of A minus. So what do you have? You have a strong and a weak. Strong OH, weak A minus. When you have both, you only care about the strong. So we do moles over liters. So here's the moles, 001 right there. The volume is the 30 milliliters plus the 50 original. So that's going to be 80. Divide those two, get the OH minus. And then negative log and 14 minus. We get a pH of 12.10, which of course is quite basic. And that happened at 5 milliliters past the equivalence point. So when you're at 30, and this is 5 past, this pH is going to be what we said before of 12.10. So let's fill that in there, 12.10. Okay, so let's quickly review. 4 main parts of a titration: the beginning, the halfway, the equivalence point, and then past it. At the beginning, we only have the weak acid just sitting in our flask right here, so we do ice and Ka. As soon as we add a drop of NaOH, we have to do stoic in moles. To get to the halfway point, we figured out first what the equivalence point was. It was 25 milliliters. So halfway is 12.5. When I added 12.5, I had exactly the same amount of leftover acid and conjugate base. So in my buffer, I did the buffer shortcut. They canceled out, and I simply had the pH of 4.74. Then at the equivalence point, everything ran out, and I had just A minus, so that was weakly basic. And then after that, I added extra OH, so I had extra OH plus A minus. We only care about the strong, moles over liters, and we got the pH. So now there's going to be a you try it on the next page. I'd like you to try that by yourself. I will make a video for it, but if you need help, you can watch the video, and then either way, check your answer at the end. Okay, we're going to work through the you try it on page 9 of the AP Chemistry Chapter 15 packet. We have a weak acid here, which is acetic acid. We're going to add NaOH to it, which is a strong base. The first thing you want to do is figure out where the equivalence point is just to get your bearings in this whole titration. So again, we could do our NaVa equals NbVb, NaVa equals NbVb. And we know the normality of the acid is still the same as the molarity, which is 0.2, because there's only one H that comes off. These other H's don't come off as an acid, okay? It's only the first H that comes off. And the volume of that we're going to use is 40 milliliters right here. They told you in the problem. So you're going to use a 0.040 here. And you know what? I'm going to use millimoles just for contrast, and it makes things a little easier right here. So anyway, that's going to be 40 milliliters. So that's going to be millimoles, comes out to be 8 millimoles. So that's how much I have in the flask. Okay, so if you want to write that over here, and then let's figure out the base. The base was molarity of 0.1. It's also the normality, 0.1. And then we're going to start to figure out here milliliters. And that comes out to be 80. 80 milliliters. So we need 80 milliliters of the base to neutralize, or should we say titrate, the acid. So this is going to be an 80. Oops, down here for equivalence point. And if this is an 80, then we know that the halfway point is going to be 40. And that's all we'll care about. Let's not even bother with any others up to there. Okay? And let's see what we got. Oops. Let's see what we got with the calculations for the first part of the titration after we do a quick sketch. So let's do a quick sketch. Again, this is going to be 7 is going to be the neutral. If we start with a weak acid, we're starting not so low, but if we end with a strong base, we end quite high. The equivalence point is over here. And you can see that that's going to be above 7. And it's not because we have a strong base, it's because we have the conjugate base of the weak acid at the equivalence point. We'll see that in a moment. So let's start with the beginning. All I have is a weak acid. How do I handle a weak acid? I do ice and Ka. Now this has to be in molarity. You've got to work in molarity. So 0.2 molar, that's all I have at the beginning. 0, 0, minus x plus x plus x. So there's an x, 0.2 minus x. I'm going to set that equal to Ka, which is 1.8 times 10 to the minus 5th equals x squared over 0.2 minus x. I'm going to ignore that. And I'm going to find out my x is 0.0019. Remember, that's a molarity. So then all you have to do is negative log that, and you get 2.72. So this weak acid starts at a pH of 2.72, which makes sense. It's below 7. Okay, let's skip down to the halfway point. The halfway point is when I've added exactly half of the amount necessary for the equivalence. So you could see that I found that 80 is going to be the equivalence point. Let me write that here just so you know. Equivalence point. And by the way, this would be an 80 right here. So then the halfway point would be at 40. And if you do the calculations for that, you're going to see what happens like we saw on the last page. I'm going to do my my Stoichkon moles first. So the halfway point, remember I got 8 millimoles of this, which means I've added 4 millimoles of that. Let me show you the calculation just before I just write that in. Let me show you the calculation. The OH minus molarity is 0.1. So this is 0.10 molar. That's going to equal millimoles over milliliters. And by the way, the 0 for the A minus. The milliliters is 40. So 40 times 0.1 is 4 millimoles. So if I have this, I'm going to only run out of the OH minus. So minus 4 plus 4. So that's going to be a 4 millimoles, 0, and a 4 millimoles. And you ask yourself, what do I have? I have a weak acid and its conjugate base. I have a buffer. So I use the buffer shortcut. So Ka is 1.8 times 10 to the minus 5th times the acid. You're allowed to use moles or millimoles. So the acid is 4 millimoles over the base, which is also 4 millimoles. You see that these divide out, and the H plus equals the Ka, which is 1.8 10 to the minus fifth. And so when you take the negative log of that, you're going to get the familiar 4.74 pH of acetic acid buffer at the halfway point. Okay, the equivalence point, it's all going to run out. So remember how this is an 8 millimoles, and then if you want to do the OH minus, it's 0.1 molar. We said that 80 milliliters was the equivalence point, and the whole point of that was that this comes out to be an 8 millimoles, and then that's a 0. So then we're going to run out of both at the same time. So minus 8 plus 8. So I have nothing, nothing, and 8 millimoles. Now, 8 millimoles is the A minus, which is a weak base. So a weak base, I have to do ice and Kb. But remember, ice has to be in molarity. So I'm going to take the base, the weak base, 0.000, sorry, I'm doing millimoles. So keep it in millimoles just to keep it consistent. So it's going to be 8.0 millimoles divided by the milliliters. Now what's the total milliliters? 120. So I'm going to write 120 milliliters because it's the sum of all the milliliters. See how I have 80 right here, and I actually had an initial 40 from the beginning. So therefore it's going to be 8 over 120, which you can figure out later. So this is going to be minus x plus x plus x. So there's an x, there's an x. There's going to be 0.067 minus x. That's going to equal kb. So x squared over 0.067 minus x. We're going to ignore that. And we're going to set that equal to kb, which remember is going to be 10 to the minus 14th divided by the Ka, which is 1.8 10 to the minus fifth. So do all the math for that, and you're going to get 6.1 10 to the minus sixth is the molarity of the OH. So then you're going to 14, negative log that, 14 minus that, you get 8.79, which is the pH, which is slightly basic, which makes sense. So 8.79 is this pH right here. Don't forget that we already found the pH of the halfway point to be 4.74. And now we're going to go past the equivalence point. Let's go 10 milliliters past it just for fun. So we're going to go to 90 milliliters. So that's 10 milliliters past the equivalence point. So again, I started off with 8 millimoles of this, but now I'm going to do the calculation for how many millimoles I have of the base. The base added is 90 milliliters. So that means I added 9 millimoles. 9 millimoles. So 0 of this to start. Now you can see that the limiting reagent is going to be the HA. And that's 0. So now look at what you have. You have a strong and a weak. It means you only care about the strong. So you're going to take the base leftovers, which is 1 millimole, divided by the total volume, which is the 90, plus the original 40, which is 130 milliliters. When you get that, you're going to get an OH of 0.0077. And then you're going to negative log it and 14 minus it, and you get 11.89, which makes sense. Very basic because we're ending with a strong base. So this 11.89 is going to be right here. Oops. And that's going to be at 90 milliliters of base added. So 30-second recap. Let's just do it real fast. You started this titration with a weak acid. So because you have a weak acid, you're simply going to do ice and Ka. The minute you drop any base in here, you're going to do stoic and moles. And what we did first is we found the equivalence point. So you can find the equivalence point with this NAVA and BVB, or you could do it like we did before with molarity equals moles over liters. All you have to do is put this moles over here because they have to match this millimoles, and then solve for the milliliters, and you're going to find out the same answer, that's 80 milliliters. So there's two ways to find the equivalence point. One is with just plugging in both of these molarities. One is to solve the NAVA and BVB. Either way, 80 is the equivalence point. So if that's the equivalence, half is 40. And when you get to the halfway point, we learned a little shortcut. You don't even have to do any work. All you have to say is at the equivalence point, the HA and the A minus are going to be equal. And so they're going to divide out of the buffer shortcut, and the H plus equals the Ka. So in the future, at the halfway point, as long as you say it's the halfway point, you could just show this calculation without doing all the ICF limiting reagent, stoic and moles. But the equivalence point gets a little tricky. So let's get to that. You've added the exact amount of the equivalence point so that the moles are the same. When the moles run out, you have 0, 0, and you only have A minus. A minus is a weak base. So you have to do ice and Kb, but it's in molarity, so you have to do moles over total volume. Do your X thing, find the Kb because you already knew the Ka, and then when you do the X as OH minus, you have to negative log and 14 minus it, so it's 8.79. So the equivalence point is the trickiest part. Lastly is when you have extra of the base, in this case, that you added, and so at the end you have a bunch of strong base and weak base. We only care about the strong. So the strong is going to be moles over liters, and that's OH, so you have to negative log and 14 minus it, and you get 11.89 as your final pH.